So I guess without any further delay, I'll hand it over to Joseph and his project Open Strings.
Hi, everyone. Thank you so much for having me at this conference. It's been really fun to see all the other talks. So I guess a little bit about myself. Technical things, I just finished my master's in music technology at New York University this May. And this project I'm talking about was my thesis. Before that, I did an undergrad in physics back in my space ambition days. But then I realized that physics is very hard and there are more applications to doing cool stuff in music with computers. So I switched to doing that. And currently I work as a software engineer at Lantern, a VPN company where we focus on providing like free access to the internet in regions where the internet is heavily censored. So China is most of our market. Some non-technical things, I play violin a lot. I guess violin is very technical, but it's in the non-technical slide. This is me. I've been doing this since basically I could walk. And yeah, I still, although I'm now working professionally as a software engineer, I play a lot in orchestral settings and occasionally dabble in conducting. So my Haskell journey has been, I took a class in C in college, and then that was horrible. And I decided that I wanted to write some code that was nicer. I read a lot about compilers, and I got to make a language in my last year of college. However, that course was taught in OCaml, and they forced us to write the compiler in OCaml. And that's when I learned that I really liked Haskell instead. I actually rewrote the teaching materials for that course in Haskell. This blog did the rounds on Haskell Weekly and Hacker News, and it was decently famous. The course is still taught in OCaml though, unless you take my version of it from my blog. So OpenStrings is ostensibly the most boring website in the world. It's a server that talks to the client, and then the client logs in and can post things to the server, which then persists to the database, and then you look for them later. Specifically, it's for music, but if that's all it was, this would be a very boring talk. The interesting part is this infer fingerings button. So if you upload this piece of sheet music, it's unclear how to play it. I mean, most violinists who are professionals will look at this and know what to do, but for the rest of us, we're like, if you're a beginner or you're a student and you haven't really been playing for a long time, you want to know what do we do here? So this is the actual live version of the website. And go look and see this piece of music. And like most people will know, for example, that you want to use 3 and 1 on this first note, but I don't know what to do after that. So if I click infer fingerings, it will think for a little bit and then provide me with the answer in the form of more annotations. If we annotate even more and try again, we'll let this run while I continue the presentation. So a quick primer on what fingerings are. Basically, violinists' left hand will use, you have fingers 1, 2, 3, and 4. I don't know if you can see my hand. Yeah, so this is 1, 2, 3, 4. And fingering is the decision for which fingers to use for which notes. Good fingerings make playing the violin easier. Bad fingerings make your hand have to distort and can lead to you playing not in tune because your hand is doing things that it's not used to, and just ruin your life. If you use bad fingerings, you'll have a terrible time. Generally, violinists optimize for being comfortable and being expressive and reusing common patterns. So being comfortable and being expressive kind of can be competing goals with each other. It's very hard to be both always maximally comfortable and maximally expressive. For example, there's in this passage, there's the comfortable version.
So that's the comfortable version of the fingering. And this is going to be the expressive one. So you get this cool slide going down, and also it's really very high up on the lowest string. Playing really high up on any string is harder than playing closer to the neck, to the nut, this part with all the pegs. But it doesn't sound as good for some definition of good that violinists have agreed upon. And so this is like a fundamental trade-off that you always have to make when picking which fingers to use for which notes. Yeah, so this is a both interesting social problem and interesting computational problem. To some first degree of approximation, there's for an end note passage, there's a 16 to the end note search space, which is really, really big. And there's even more possibilities when playing chords. So I can try maybe some part of the website will continue working. Can visualize kind of like the number of possibilities with this button. This is only for the first measure. Well, that's working. So yeah, besides that the problem is computationally hard, humans don't have like social agreement on what constitutes like the best possible fingering for a passage. This section of sheet music is quite, it's simple because it's just a series of scales. The scale goes down, the scale goes up, the scale goes back down. But a lot of different editors who are all famous violinists don't agree on what to do. And none of them is, right, but since none of them is right, and there is no right fingering for everyone, the algorithm has to reflect that. So there's a bit of prior art in the form of these 3 papers on algorithmic fingering selection. The first person to do it is this guy Saye in '88, and he formalized the problem as like a Markov chain. And the big advantage of treating it as a Markov chain is that the Markov chain says that only the fingerings immediately preceding the current note should influence the fingering of the current note. So that reduces the search space by a lot, because you don't have to consider like every possible configuration of fingerings when thinking about an end note passage. You just have to think about like one slice of the passage at a time. And then this paper by Maezawa, they have, in addition to looking at sheet music, they look at recordings, and they try and infer from the recording what fingerings people used. And then the most recent research was that they would add an extra parameter for skill in order to kind of differentiate good fingerings for beginners and good fingerings for adult violinists or professional violinists. So for this work, the big motivation to improve on these prior papers is that everyone should be able to use it. This is the first version of this kind of thing that I know of that actually is on the internet that you can go use. This operates directly on Music XML, which is a very common export format for different kinds of score writers. You can, it's very easy to read. Like this is what sheet music looks like for everyone, and violinists will know what this is, as opposed to something like MIDI, which only encodes like pitch and duration information, and therefore is not really renderable into a piece of sheet music that you can read without listening to. And the configurability aspect. So the paper, one of the papers, they add a single parameter for skill level, but there can be 2 equally skilled violinists who disagree on fingerings, as we saw from the edited example. And users should be able to say, hey, I like to use my pinky less. Please generate a fingering for me that uses the pinky less. Yeah, so the implementation has a lot of challenges. In addition to like the computational complexity, Music XML schema is really large. It's like generating a Haskell type from that captures the Music XML schema is possible, Typing it by hand is certainly not a thing that I want to do. And there is a library that generates like code from the XML schema. I think it's called Thatno XML. It's on Hackage. But I feel like this is the kind of thing that like Clojure programmers make fun of us for trying to do. And so, and they always like make up like, oh, a straw man Haskell programmer, they can't get anything done because they try and use too many types. And so while it's possible, we can instead just give up, so to speak, and treat XML like everyone else treats XML. And it turns out that we still have really, really, really good tools for doing this, like, Lens. It's a big, deeply nested structure that has lots of elements that we don't care about, and only specific ones that we do care about. And so it's really the perfect use case for Lens. And if Chris Penner is watching this, thank you very much for your optics book. I really learned a lot from it, and I could not have implemented this without reading it. Yeah, so more concretely, the problem structure is this kind of graph where each vertical slice represents a single time step. A time step can be either 1 note, 2 notes, a chord of 3 notes, or a chord of 4 notes, or it's a rest. Now that this graph is loaded, we can see that this is for the first measure. This graph over here represents the first 5 time steps, 1, 2, 3, 4, 5. This is the D and F sharp here. Then this note is just a rest. And then this section represents every possible fingering for this guy over here. You can use 3 on the G string and 1 on the G string. Oh, sorry, that's not the right. You can use, 3 on the G string and 1 on the G string. Sorry, Roman numerals are strings and Arabic numerals are fingers and letters are the note, the pitch class. If anyone has any questions about what anything means, please feel free to interrupt and ask. But yeah, so every node in this vertical slice kind of is a different fingering for the same time step. And darker colors indicate more expensive in some sense configuration, and that will kind of drive the algorithm to find the shortest path. But yeah, so given the Markov assumption that we assert for fingerings, the reason that they only have edges like this as opposed to an edge, say, from here to over here, is that we only consider fingerings in adjacent time steps to influence each other. It turns out that this is sometimes not exactly correct, and we'll talk about at the end, like ways to maybe think about relaxing that assumption or overcoming some of the problems that it induces. So in addition to having costs for each node, there is a weight associated with each edge. That Haskell type is something like this. You have a penalty that either is for 1 node or for 2 nodes. That would be adjacent in the graph. And there's some cost associated with that, and a weight that the user can drag a slider in order to configure. So that set of sliders looks like this. They want to make the same string have a high negative weight, they drag it. If they really don't like playing in the same position, they can move this up to make it more expensive. If they hate using their pinky, the 4th finger, they can drag this all the way over there so that the algorithm really penalizes it quite hard. And that corresponds exactly to this p-weight field. In practice, initially when I wrote this, the cost was just double because I didn't see the need to make it polymorphic, but it turns out that there is a library on Hackage by Ed Kmet called ADD, or for automatic differentiation, that if you make your thing that you want to differentiate over polymorphic or some instance of num A or the num type class, then you can get automatic differentiation for free, just like Python. Yeah, and this is just a kind of screenshot of what the weight adjustment looks like. Yeah, so an example penalty. So this is the penalty 1 for a single node in the graph. It says is called the fourth finger penalty. It has, if the, basically this is a binary activation thing. If the fingering on that note is a 4, then yes, and otherwise it doesn't activate at all. And then similarly, this is a penalty 2 for 2 adjacent notes. So if the 2 adjacent notes are on the same string, yes, otherwise, other cases we allied here. But if the 2 notes are on the E string and the D string, then this penalty doesn't come up. Penalty can be kind of like a misleading name, because like same string is usually a good thing, but in that case it would just be like a negative penalty, and negative bad means good in this instance. So one of the reasons that people don't traditionally use Music XML to do this kind of analysis is because Music XML is complicated. Not only is it like a big schema in order to represent like the 300 years of musical information that we've encoded into sheet music over time, but it's not linear. So there's backup and forward elements in addition to note elements in order to support music that looks like this. So in Music XML, this would be like, this first measure here would be a measure followed by, inside the measure would be this rest, and then this note, and then backup, something called backup 4, which would move the clock back over here. And then there would be in a new voice, this note, and then this note. And then it would start again with the next measure, and there would be the same thing. Note, 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 backup, no, 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 no. And for the computer, we really want to have like contiguous slices. At any point, I want to know exactly what fingers I need to put in what places on the fingerboard. So we have to do some kind of pre-processing to turn this into this. Also, there's notes that are called grace notes, which in print just appear as much smaller notes behind, or in front of big notes like this. Due to some accident or misinterpretation of them, they have 0 duration, which in practice obviously isn't true, because then you wouldn't hear them, but that requires a bunch of other maneuvering. In order to deal with this kind of complexity of XML, we have lenses, and they're very helpful. So they're the only notes that we care about for the purposes of figuring out what time steps are is the note element, the backup element, or the forward element. And this kind of statement is equivalent to writing in JavaScript. This would be like document.query select or all something like note backup forward. Except that whereas in JavaScript they have this hard-coded for XML or HTML, in Haskell we have it for anything that's something called plated, which is a type of lens that lets you recurse into some arbitrarily nested tree structure. The harder part is going kind of back. Once we have these elements, we have to shuffle them around into the time step type from over here, where the note has an XML ref, which is like an int for tagging and the actual XML element. And there can be notes that live in these things that are not necessarily like corresponding to XML elements that live next to each other. So this is the mountain of code that does that. It uses a bunch of tricks. We have the ST trick in order. So what it does is that it keeps a track of time, and then it pre-allocates a vector for the length of the passage of rests. And then there's like a semigroup or a monoid instance for notes for time steps, where 2 single notes with the semigroup operation is a double stop, 2 double stops is a quadruple stop, and then the rest is the identity. It's not a lawful monoid, because if you try and combine 2 quadruple stops simultaneously, it errors and says that you can't play that, but that's the cost of having a real instrument and not having 8 fingers. But yeah, so it's nice that we are able to mutate vectors like this in Haskell. And this is how one of the ways that we are able to get around like being a pure useless language, and that we're actually very useful, and we can reach for these types of tools if we absolutely need to. Another way to do this could have been with like a sequence or just a list, but that would be less efficient because it requires random access and moving around the index of the vector. Initially, I tried to use something called a pretext, which is like a lens that's already been applied to a structure. I asked about this on Reddit, and I was told that this is actually not possible because I wanted to apply the modifications back into the structure from like after taking each element, putting a fingering on it. I wanted to put those elements back into the document, but because the pretext is already applied, you can't do that with like multiple pretexts into the same document. So I asked this nice question, and then this person captured what I had thought about it. My thoughts, had I read this question like a month before I learned about lenses, I would have reacted like this guy. But I fell prey to the normal Haskell trap of, oh, now I understand this thing. I can go write a Monad tutorial. Here are some of the results that I got for common pieces. And this is what I used for the survey when I wrote my thesis. I asked some violinists what they thought of this. Quickly, because I know not everyone's a musician. This is a good I think this is a good fingering, and I'm happy with this. The only problem really is over here, this series of 4-2-4-2-4-2 is a little harder to play than something like 3-1-3-1-3-1-3-1-3-1-3-1 would be. Just because the pinky is generally weaker. But besides that, it's quite good. This Bartok passage also was very favorably reviewed. It's got a lot of like accidentals, which makes it annoying for humans to look at and finger and think about playing, but for the computer, it doesn't care. So it did a pretty good job. And then the final example that I asked people to rate was this Isai. Isai was a very famous in the early 20th century violinist. This example is a lot longer, but it does some questionable things like in this section, for example, it switches, this note is in first position, and this note is in third position, and this note is back in first position. And this is where the Markov assumption we were talking about earlier kind of screws things up, because if we see in the graph, the 1, 2, 3, fourth note is open, and between an open string and any fingered note, like this note or this note, it's a totally free transition. Like in principle, you can play an open string and then your left hand is totally free to move around anywhere it wants. And then, so you can just put it anywhere. However, in practice, when you play the violin and you play an open string, your hand doesn't just kind of leave totally. It just stays where it is, but the finger gets lifted. And so the Markov structure here doesn't model that at all. It treats like what happens in this note and what happens in this note are totally unrelated given what happens in this note. So this is why like this fingering, the algorithm suggests kind of nonsense where a normal violinist would say, oh, I want to I've lifted my hand off of this note. I'm still not going to move my hand anywhere during this note because I can put a 3 here and be in the same position. So that fingering got poorly rated by the participants. And yeah, so this is the data. There were only, like 10 or 12 people who took the survey, which is not super great, but it was an expert survey of expert violinists. So there's a lot of us, but it's not like you can get humongous sample sizes. In any case, though, so the Bartok, which is the second one that we saw, was rated very highly, or it was not correctly guessed by the participants that a computer made it, because it's good enough to pass this like Turing test. These three examples were some that I wrote, and as we can see from the theme is that humans don't agree on fingerings, and there's a few humans who dislike my fingerings, which is fine. But yeah, and then so clearly this one has a lot of work. No one was convinced, and this one, I'm not really sure why no one was convinced, but they weren't. Yeah, so because this was a research paper, we also had to compare with the other papers we cited. Given the same example, the advanced fingering, this is the paper, but by the way, that had the single parameter for skill levels. So for their advanced musician, they inferred this fingering, which in this circled part kind of falls off. I think that most people would agree to use a 1 here instead of a 3, and that this shift is awkward. Whereas this algorithm correctly shifts here, and here it doesn't shift from this note to this note, and instead shifts on the open string. So whereas in the Zai example, that was a bad thing to shift on open strings, here it's how everyone would do it. So I think a way to get around that would maybe to have like the fingering inference, like the cost functions work in some kind of monad that keeps track of like the state of your hand and not just the single finger that's pressing down on the string. But I'm certainly excited to hear anyone's ideas about what could be done about that. And then for the beginner configuration for this paper, they inferred very good results that just stay in first position and use a lot of open strings. Whereas the penalties that I wrote, I didn't really account for enough the beginner preference to stay in first position only. So I do some things like go higher on the A string. But in principle, this is like overcomable by me just sitting down and writing more beginner-friendly cost functions, which I haven't done yet. And then this, please excuse this giant block of notes. But this is the one that does fingering inference with the addition of a recording. And so this is what they got for like a really, really old wax cylinder recording. And it makes like terrible, terrible assumptions, like that it should play notes that are very high in the staff on the D string, which is like you're poking your neck already with your left hand. And it does this like sustained for several measures. And this is like I'm very confident that no violinist has ever intentionally played this. Whereas even though this algorithm doesn't take into account any kind of recording because you can't upload audio to it, it still correctly, for the same passage, puts you on the E string, which is where everyone played this passage. Yeah, so I'm happy with how the thesis came out. I think there's some obvious improvements. First off, as we saw, the algorithm took a long time to do things. So optimizing performance is important. This is hard because there's fundamental limitations on how fast you can search this graph. I think algorithmically for an acyclic graph to find the shortest path takes time, like order of number of vertices plus number of edges. And as we can see from here, there's like a lot of edges and they're hard to like even render on an SVG. But it's certainly possible that we can do some more aggressive pruning on the edges, say for like if a node is particularly expensive, we can just cut off all its edges and just get rid of it. Yeah, so this point ties into like remembering the state of the hand during an open string or during a rest, to get around problems of moving the hand to somewhere else when it doesn't need to move. And then, so the current process of like adding a new cost function is that you can send me a PR. I will, of course, review your PR in a timely manner and integrate it. But for someone trying to like interactively try out new penalties, this is obviously unacceptable. So either like there are different ways to do this. We could use like a Haskell. I think there's some paper that lets you run or talks about letting you run like Haskell plugins. Letting arbitrary people send you code to run on your server is a little scary. But maybe if we like compile to WebAssembly, we could have other people compile to WebAssembly and then run on their machines. So it's less, less scary than arbitrary code execution on the server. Or there's the direction where we just release this as kind of like a hackage library with some base penalties in already there, and make like a desktop version so that everything runs on the user's machine and they can run whatever they want. The fact that the penalties are in Haskell is like great for us, and we love writing Haskell, but the having violinists who want to try new penalties write Haskell can be daunting. But that they can learn Haskell. Everyone should learn Haskell. And then of course, like, I spent a lot of time writing this. I would like to make money off of it someday, but I'm not sure exactly how I would do that without totally just having people pay for it. Yeah, so thank you all very much for coming to this conference. I'm glad I got to present it, and I look forward to talking with you guys in the spatial chat.
Would you have some time before a spatial chat? There were a few questions on the analysis.
Oh, yeah.
So there was one that says, can we assume that probably a computer equates to bad and probably a human relates to good in that?
Yeah. So okay. The like survey evaluation.
Yeah.
You're right that I could have phrased it. Humans, violinists, I imagine, tend to think that human-generated fingerings are better. And so, yes, the answer to your question is definitely yes.
Gotcha. And then there was another one. Was there a sort of comparison with the human panel on, I guess, the same piece, but with the weights set differently?
No. I didn't do any surveys of that. For the survey, I ran the inference with like a couple sets of weights to see which one generated the fingerings that I liked the most, in an attempt to fool the survey takers into thinking it was a human. But definitely, yeah, there's certainly a lot of future work can be done with like more in-depth surveys and talking to people just like at greater length about what they liked or didn't like about the process. This was like a thesis during COVID, so I never like met any of my survey respondents. Certainly though, like when orchestras get back to working together, I'm gonna definitely bring my laptop and force people to look at this thing and tell me what they think.
Cool. Yeah, there was a comment that maybe the survey people disliked the fingerings that you preferred and concluded as a result that they were computer generated. That was a comment.
I didn't include these slides over here, but I did have more survey results. I had just elided them for time. I had people, in addition to rating them like on this Turing test, I asked questions about like, how comfortable do you find this fingering? And this is the same set of pieces. So here we see that like people found these very uncomfortable, and people found this somewhat comfortable, though they thought it was generated by a computer. And the Bartok scored well. And again, someone disliked how comfortable my fingerings for Bruch and Strauss were. Kind of similar results spread for the expressiveness of a fingering, which is kind of like a vague thing to rate on, but makes sense in like lyrical passages. You want to stay on one string and do some kind of fancy slides to make it sound more soulful. And again, we see like Isaiah scores badly, Bartok scores fine. And this is kind of like a bad question for the Bartok anyway, just because the Bartok is very fast and it's hard to play expressively. And then another question I asked was like, how idiomatic do you find this fingering? And this is where people didn't like the Prokofiev as much, because although they found it to be like reasonably comfortable, they found that it was not really, it wasn't in line with like agreed upon best practices of not using the 4/2, for example, the whole time. If that addresses your question about
that's cool. Is there is this online somewhere that if folks are interested, they'd be able to see some of the, I guess maybe like a resulting analysis page or something, paper?
Yeah, so the thesis itself is on the GitHub page, is linked on the GitHub page of the project.
We can post it in Discord. Cool. I guess one last question, then maybe I'll toss it over to the spatial chat. Is I asked you this earlier, but is it easy to adapt for other stringed instruments? Or maybe if not, maybe what would sort of change?
Yeah, so right now it's hard coded for strings named G, D, A, and E. We could just unhard code those to be like Roman numeral 1, 2, 3, 4, and then it would work for viola, modulo some like more. No, I think that would just be the amount of diff it would require for viola. And then for cello, it would, the same process would work, except that a lot of the penalties wouldn't make sense anymore because the distances between notes is a lot bigger. Bass, even worse version of the same problem. But yeah, so once like we add user configurable penalties, then you can just like, and fix the issue with hard coding string names, you can basically just add your own set of like base penalties, and then it will calculate weight, edge weights based on those, and then it will work. For like a guitar, right now the strings are like, they live in a sum type that just has forced constructors. I guess we could change that to be like a nat or something. And then again, a similar thing with the penalties would work fine. For something like piano, it becomes like way harder because you have two hands and the whole model is really different.
Well, if anyone has any other further questions, I think we'll toss it over to the spatial chat. But thank you very much, Joseph. It was fascinating. I did not know that this that research existed before. That's very cool.